Welcome back. So, previous lecture we were discussing about the colluvial wedges. Now, this is again our experience that sometime in the trenches you will not come across a correlating sequence on either side of the fault, and also the well defined what we were talking about, the colluvial wedges. Now, this is an example which shows the very low angle thrust fault which has resulted into at least 4 earthquakes along this. That was been identified based on the trench which is exposed here. This trench log shows at least 4 earthquakes along this. Now, the point here is that you don't see the comparative sequence on the footwall side, and there's the hanging wall, but based on the soil formation, because the soil formation will help you in identifying that this was the previous surface which got deformed and then subsequently capped by the next depositional event. So, based on the soil also, and that's what we discussed in the initial lectures, that understanding of soil formation and all that is important when we are interpreting the events. So, this shows that this is the event 1 along this one, okay, and so the oldest event. Then event 2 was, because we have the 2 soil units here, so at least those 2 soils were been displaced. However, we don't see the sequence. Probably this 2 layers are sitting far away in the deeper part of the footwall. So, this is an event 3, that is in the next event. So, what we see here is that no comparable sequence is seen on either side of the fault plane. So, there is no need to worry for that, but a close interpretation or the understanding of the sequence of deposition can help in identifying the events. So, only the borehole data suggests maximum displacement of the fluvial cobbles. Okay. So, if you take the course here which has been shown here, that you have this portion, that is the fluvial material of comprising of coarser deposits were sitting far deeper, which were not been encountered in this section. So, sometime you can do this, but this is again going to be very expensive exercise, but you can, based on this, at least you can understand that in the thrust faulting you have the older sequence overriding the younger one here. So, 4 events were been identified, and those were based on this 2 soil units and then 2 colluvial material which was been encountered in this trench. So, based on this, so this was this colluvial material which is also faulted along the fault was represent the second earthquake, that is penultimate earthquake, and the final latest one was along this, and which suggests the formation of this colluvial material. Now, usually in particularly in Himalaya, this what I was explaining earlier, that you will have a very typical low angle detachment, and you will see the imbricated fault system, and this can be explained with the help of if you bulldoze the material on a very low angle surface, then you are bound to see the imbricated faults which are coming on the surface, and you will see the younging sequence, that is, you will have this one is older, this one is younger, and this is the youngest. Okay. So, the deformation is getting younger towards the foreland side. So, this is a typical, or we can say idealized pattern of deformation which is seen in Himalayas. Now, there is another presentation which I borrowed from Mustafa McRoy from Strasbourg, IPGP, and which were the studies were been carried out on the Alasnam earthquake. So let's see that how we see the geomorphology and what we encountered in the paleoseismic studies and how the deformation pattern varies along the fault. So this portion is from the this region particularly, where we have the deformation along the Alasnam earthquake. So you have the Algeria is sitting here. So we have the similar tectonic framework which we see in Himalayas. So this is a part of the alpine Himalayan range. So the very clear-cut fault is been seen on the surface along this plate, the plate boundary between these two plates we have, and the slip is, that is the convergence rate, is around 4 to 6 millimeter per year. So you have like the fault system which has been developed here as well as along this line. So the strike of the fault changes in different segments. Okay. So you have the fault trace which runs here, and this is the close-up image of the Lancet image, very old one, 1977. So it shows the trace of the fault over here. It goes like that, okay. And the different segment shows different pattern of deformation. So segment B and A, the strike is not the same. Of course, they belong to one same fault system, but the strike is differing in segment 1 and segment B. And then you have the segment C also, the strike is slightly different. So you have this they have marked at a different sequence. So the major deformation was along the thrust fault, which has been shown here, and this was the typical folding which was experienced in form of the fault scarp on the surface. So the Alasnam earthquake was on 10th October, and that was, the magnitude was 7.3. So this is the same sketch which has been shown, that you have the low angle. So at the base you have high angle, and then it becomes the low angle towards the surface. So typical of fault bend folding which has been seen and experienced in Alasnam earthquake. Now coming to the different segments, and what they did was they carried out a detailed mapping along these different segments where the strike is not the same, strike varies, and what type of deformation they were able to encounter in different segments, segment A, segment B, and segment C. Now coming to the part of the geomorphic and the drainage control because of the Alasnam fault, what was been identified that because of the folding there was a damming of the blocking of one of the channel, as you can see in the previous slide here, that you have the stream which was blocked because of so this blackish portion is shown as the stream here. So this cleft or the formation of the anticline because of the deformation along the low angle fault here resulted into the formation of a pond here. So this shows that this channel was disrupted and blocked because of the natural dam and temporary faulting by the anticline. Okay. So this portion remained as a poorly drained area on the thrust foot wall. Okay. So this was the hanging, this is the hanging wall, and this is the foot wall here. So this was because this process was experienced because of the 1980 Alasnam earthquake, and they also like identified in the trench that similar phenomena has occurred in the past also. Okay. Now, along with that, they also tried to look at the different deformation pattern in segment 1, segment that is A, segment B and segment C, because of the change in the strike. So, the deformation blocked the channel here which was flowing. So, you can see this was the main channel which used to cross this, and this is your hanging wall side and this is your footwall side. Okay. And this resulted into the flooding in this particular area. Now, similar earthquake, as I told that they were able to pick up the similar type of sequence, that is your lake deposits or because of the ponding condition in their trenches. And also they were been able to pick up some paleo channels here. So, this was the pattern of deformation. So, you can see the scarp here, the one scarp is running over here, another is which is seen a very blurred image, but you can easily make out the scarp which was developed in this area. And then we have a very clear scarp which was developed on the one side. Okay. And another one also very similar to what we were talking in from the Kutch. Okay. So, you have the collapsed material and dragged along the scarp. Then along with that, what they were able to pick up was that some oblique movement which shows the strike slip. So, lateral movement was also picked up along the fault. So, this shows the boundary here which is shifted here along this fault line, and then the scarp here. So, leveling profiling across the scarp, what they did, so they measured the displacement of the surface at various location, and the 2 meter of displacement was experienced in 1980 Alasnam earthquake, whereas the cumulative displacement of the surface was around 7.1 meter. And in some places like here they identified 2 meters, in some locations they were able to see 1.5 meters and so on. Okay. So, what this suggests that the extra height which they encountered at various locations, okay, was because of the previous earthquake. So, this shows the cumulative displacement, because this they were able to pick up from the recent rupture. So, it was very clear. So, they were able to pick up with that, but the actual height of the scarp, when they did the topographic profiling, then they were able to pick up that it was comparatively larger than what it was experienced in 1980 earthquake at various locations. So, this suggested that they had the cumulative displacement which is manifested at the surface. So, cumulative movement visible at different location along the fault, assuming a characteristic behavior, they observed an average 3 times the 1980 co-seismic displacement. So, that they inferred initially that if you compare the cumulative displacement and the displacement which took place at the time of the earthquake, 1980 earthquake, then it shows at least 3 times more the displacement observed in terms of the offsetted surface. So, the objective of the paleoseismic investigation usually remains the same, that so what they did was to identify the paleo earthquakes or the ancient earthquakes. They investigated the marsh area which got flooded. So, if you are having, for example, this what they were showing, that this was the stream which was flowing for example like that, okay, and then there was an uplift here along this fault. So, it blocked this channel So then what they were able to identify was that this channel did not cross here, and because of this warping they saw that there was flooding here. So ponding condition, definitely if the cumulative scarp which they saw was more than greater than 2 meters, okay, because the 2 meters was approximately the average displacement which was been picked up in 1918 earthquake. So it was more than that. The similar phenomena would have occurred in the past. So the investigation was on the marshy area, trench the main fault scarp, and document successive displacement, measure vertical offset with the leveling. So what they did initially was that they identified the offsetted area or the displaced area. They did the profiling of that area. Based on that, they were able to identify that they had the cumulative scarp. So the trench was across the main fault scarp to document the previous displacements. So this was the area where they put the trenches. Multiple trenches were being opened up in the region, and that gave them clear indication that the scarp, cumulative scarp which they identified, was not because of the single event. Okay. So the multiple trenches were being dug across the scarp here. So this is the scarp which they identified. Okay. So thrust fault in trench and reconstruction since last 1,000 years. Okay. So that what they saw. Okay. They have, like, this is one unit which can be clearly picked up, and another matching is this one here. So of course that what we have been discussing, that the older one will show the maximum displacement. So, and finally what they have is the displacement of this material here on the surface. So this was 1980 rupture. So as you will come across that you have the maximum offset, and that shows cumulative offset of the surface. Similarly, in the trench you will have the older units will get displaced, will show more displacement as compared to the younger ones. So these are the different units which they have been picked up, but this was the most prominent one, which goes something like this here. Okay, and this unit you can pick up over here. And then finally what you see is this one. Okay. Now if you reconstruct this, then what you will be able to talk about, that the fault existed before this event. Okay. So you had some scarp which was present there along the displacement along the fault. So total 4 events they have been able to pick up. So if you see the event 1, buried fault below unit B. So you have unit B here. So you have the buried fault below unit B and A. So these are the 2 units. I am sorry for the image, it is not clear, but this is B and this one is C here, and then you have A here. Okay. So event 2 reactivated displaced unit C scarp deposition of the, and then so this was been displaced. Okay. Either you take this as an A, B, C. Okay. So if you take this A, B and C, that what it says, that this scarp which existed at the C scarp, and then finally the deposition of unit D. So you have now the A, B, C and D here. Okay. So the next phase after the faulting covered the event 2. Okay. Then we have, like we see here, that we have A and B and the C, D, E and F here. So event 3 displacement of unit D. So, this was displaced. So, you have the displacement of unit D because the event is occurring after D. So, then you have the displacement of D, and then you have the deposition and the displacement of E also in this sketch which has been shown. But the second event was after the unit D. Okay. So, event 3, displacement of unit D followed by erosion of D on the hanging wall side and deposition of unit E and B. So, in this phase of deposition you will experience, okay, a deposition of unit E and F. Then last one which displays the complete sequence. Okay. So, fault throw increases with 1980 event faulting and folding the unit E and F. Okay. So, you can regenerate or retro deform the sequence in this way of any trench. So, I'll show a better example from the trenches which we dug in Himalayas, that how you can reconstruct the events and identify the paleo earthquakes. So, this is the same sequence which we were discussing in the previous one. So, you have different events which were been picked up, at least 4 events were been picked up in this small trench. So, along with this you will also come across the secondary faulting, and this was another trench which exhibit just the warping, but the formation of or the development of the secondary faults, and this displacement along the secondary fault helped in identifying different events. So, another trench, it explains again the earthquake of Alasnam. So, having high angle and then getting into low angle, displaces unit the fault A, this fault A displaces the beds CL I and RU. So, you have the RU and you have the CLI here, okay, and created a fault propagation fold. So, it did not reach right up to the surface, but it created a fault propagation fold, and BU unit post faulting deposition. So, you have post faulting deposition here, and then the displacement of the event. So, the deformation was the next event again displaced or took place along the same fault, but along with that 2 subsidiary faults or the branching out faults were also developed, and they also displaced the events in or the faults or they displaced the units at the lower portion. Okay. So, renewed faulting was along B. Okay. So, you have the another fault which came right up to the surface was the branching out fault from fault A. So, you can either like identify that the different faulting events along the different fault strengths. So, fault B displaces BU and BCS. Okay. And along with this, new subsidiary faults, that is your NR, forms near the beheaded part of unit that is fault strand A, and that also displaces the older units. Okay. So, finally, what we see is that the most recent earthquake did not slip the material along the fault strand B, but it again got reactivated along fault A. Okay. So, this old fault which was this was the first, and then the branching out fault came in and displacing the younger sequence, and then finally what you see is that fault B did not take up the slip, but the most recent earthquake was along fault A. So, though the fault B is the younger fault compared to A, fault A was reactivated during 1980 Alasnam earthquake. So, we have to be extremely careful talking about that which fault strand has taken up this slip during the recent event, and that can be done based on the cross-cutting relationship you will examine in the trenches. So this is another example of the cumulative movement, that is an offset which they were able to pick up along one of the fault trace in different segment, which shows the right lateral strike slip movement. Now coming to the Indian part, if you see, okay, then we have the most active region which is sitting in this zone. There is a northern portion, and that marks the plate boundary between the Indian plate and the Eurasian plate. Okay. So we have like incomplete record, I would say, rather, but to some extent we have the historical data which shows that there were earthquakes based on the damage and all that, but recent studies have helped us in identifying the ruptures of at least these three events. Okay, two were very recent, so we know that what happened. Even the Kashmir earthquake of 2005 was along the earlier identified Thunder Fault in Pakistan, and 2015 remained blind, but this was along the Himalayan frontal thrust. But we never have the idea that where exactly these two earthquake, on which fault this were been triggered. So we have some understanding taking into consideration the ancient earthquake. All these three were in 20th century, but again no surface ruptures were been identified till last recent years. But in last 4 or 5 years, many paleoseismic studies have been able to identify this rupture. So this two, 1934 and 1950, were along Himalayan frontal thrust, and this was been believed that this was along Himalayan frontal thrust, but this is not along the Himalayan frontal thrust. So I'll talk about this, at least this earthquake, and what we have been able to pick up about the ancient earthquakes which have occurred in this region. So now, with having this understanding and what we see the earthquakes which have occurred in different regions along this, what we have is the macro seismic zonation. So this is a seismic zonation map which shows the different zones, that is zone 5 is red, and then zone 4, zone 3 and zone 2. So the blue one is your zone 2, and we don't have zone 1 now. This was been modified after 2001 Bhuj earthquake. So I'll stop here, and I will continue in the next lecture.